All right, so now we're going to get started with Gauss's law, okay? Now, I don't know if you've heard it before. To be honest, when I first learned it, I've never heard of it before. But what this does is basically help you find electric fields, okay? And find a flux, an electric flux that passes through a closed surface, okay? Now, and for this, we basically have two equations, all right? The first equation, which is the one that we can see right here, okay? And I'll get to this drawing in a bit, okay? Just bear with me. The first equation is basically the sum of all of the charges, which is this Q, enclosed by a certain surface, and then you divide that by a constant, which is known as epsilon naught, okay? And that's basically the easy way for Gauss's law, but as you may know, we're not going to work with that, okay? The one that we're basically going to work with is the second equation, okay? And that is going to be once again, the sum, well, the integral of a closed surface, okay? And what this is basically you add all of the electric fields, which is E vector, on the Gaussian surface, and the dot product, okay, of the dAs on that surface. Okay? Now, to that, you add this closed, well, to this original equation, you add a closed surface integral, and it has this circle in the middle because it means that you add every electric field as well as every dA on the surface. Okay? Now, Gauss's law can sometimes be represented as a combination of both equations. Okay? That being the sum of all charges, which is what we have over here, divided by epsilon naught, which once again is a constant, and that you can sometimes see it equal to the closed surface integral of E dot product with dA. Okay, so I'm going to go ahead and erase this over here as we now have it up top. And okay, we can use this, for example, let's say we want to find the E vector for a point charge, okay? So here we have the charge. We have a positive charge right here, okay? We have electric fields, coming out at all angles, all right? So actually, I'm going to go ahead and erase this. I might have spoiled just a little bit, but bear with me, okay? All right, we have here this charge, okay? We're going to call it Q. And, well, as you know, it has electric fields coming out in all angles. Okay, over here, over here, over here, and over here. And once again, this is in a 2D dimension, right? But it's actually coming towards you through the screen, going through the back of your tablet, phone, computer, whatever. And yeah, so it's going all around, okay? And well, what we want to find is E, which can be at any given point, all right? So we're going to go ahead and draw E, I don't know, right around here. Okay, that's going to be E for us. Now, for this, what we draw is a Gaussian surface, okay? And a little bit like from what I spoiled a little bit ago, you can kind of have an idea of what we're just about to draw. Okay, so let me just connect this. Okay, so what we draw is this. And this is a Gaussian surface, which is basically just like a sphere, right? And what we have now is a representation of Gauss's law, okay? So what we do is we have here the formula that we previously wrote, okay? We have Q, over epsilon naught, okay, which is equal, I'm just gonna write it down just a little bit better, to the closed surface integral of E vector dot product of dA, okay? Let me just erase this. Okay, now the left side of the equation is done due to the fact that, well, epsilon naught is a constant, okay? And we already have, you know, Q because it's the charge that we have, okay? So working with the right side, we can actually get rid of the dot product because the dA of the surface, which is a little sample, as if you can imagine, or just a little tiny section of the surface, which is actually infinitesimally small. So this is way too big to, but it's not drawn to scale, okay? Imagine that it's zoomed in. So what we have here is the dA is going outwards, okay? And because it's positive, the electric field is also going outwards, okay? So because these two are parallel to each other, okay, we are able to get rid of the dot product, okay? They are parallel, to the Gaussian surface. And this is a very important step because for you to be able to go forward with this solution, we do need to get rid of the dot product, okay? So this is one of the ways in which we are able to get rid of the dot product. So now we can just go ahead and write, here, let me just erase this. Okay, so that would be E times dA, okay? So that's a very important step, okay? So now, because E is at the same, or is the same at every point of the surface, you know, because the electric field is going out in all direction, E can be pulled out of the integral, okay? So what we have now is equal to E integral of dA, okay? Now we have the same left side, you know, so we have Q over epsilon naught, okay? Now, to be able to do the sum of all dAs, we can use the formula of the surface area of a sphere, you know, because that's what we're trying to be able to calculate, okay? And that is equal to 4 pi r squared, okay? Now, if I'm able to bring that to the other side, okay? So we're talking about leaving the E alone, okay? The sum of all the dAs, I'm referring to this part specifically, okay? So once I bring that to the other side, I'm left with the formula E is equal to Q, which is up top. And then we have 4 pi epsilon naught r squared, okay? So now 1/4, which is what we basically have here, pi epsilon naught is the same as K, okay? Now K is the same as this little section, okay? Which is what I basically just said, okay? This little section right here, okay? So now what we're left with is E over here is equal to K Q over R squared. All right, and now that's basically the fundamentals of Gauss's law, or the very basic fundamentals. And with this, we're able to solve a numerous amount of problems, and a numerous amount of different solutions are provided with this law. You know, a lot of them relating to Coulomb's law, okay? Which is basically one of the transitions of this formula right here. The one that I'm highlighting or showing right now, that's Coulomb's law. And that's how one of the ways in which we can transform Gauss's law to Coulomb's law. Okay? So we'll go more in depth in a next video, but thank you, and we'll go in depth a little bit later.